So welcome everyone to our ITC Instructor Training Center Introduction to Networks course for this week, and it is the week of November the 1st. So we're now in November. You can officially start listening to Christmas music and not be too embarrassed about it. Of course, my wife started on, I think, the 29th of October, and so she's ready for Christmas and has been. But we are going to get started this week and talk about Ethernet, and we're moving from our discussion last week where we discussed access methods and we discussed layer 2 of the OSI model. And we talked about the media access control and the logical link control sublayers, and we'll talk more about those in this particular section. We're going to talk about a particular layer 2 technology, which is Ethernet, which is really taken over in almost every environment. Ethernet is a protocol specification at layer 2 that can run on multiple different types of physical connections. We talked about fiber optic cable. We talked about unshielded twisted pair or any type of twisted pair cabling. We talked about coaxial cabling, Wi-Fi, microwave, any of those. Ethernet can work on it because Ethernet really doesn't have a definitive physical layer specification. It can run across many different types of standards, standard medias, depending upon what 802.3 level you're running. It also has the ability to run at many speeds, everything from it started at 10 megabits per second and went all the way up to 100 gigabits, and now we're actually getting faster than 100 gigabits for Ethernet, which is kind of neat. One of the things that we do have in layer 2 of the OSI model is this MAC or media access control sublayer and the logical link control sublayer. It's important on these two items that you understand that the MAC sublayer deals with our physical addressing. It deals with our media control, media CSMA CD, how you put items out onto the physical layer. It deals more with the hardware-based items, whereas the logical link control is that layer that can be used to connect to the network layer. So there can be an LLC sublayer that talks to IPv4 and an LLC sublayer that talks to IPv6. So anything that's an LLC is software. So it's the NIC driver program that interacts with the NIC, the MAC sublayer, and the physical layer. Those are all part of the LLC. The MAC layer is that lower level that deals more with the hardware specifications. So in the MAC sublayer, we deal with frame delimiting, in other words, start frame delimiters, frame check sequences. We deal with addressing, which in our case, we're going to talk about media access or MAC addresses, media access control addresses or MAC addresses. We talk about error detection, which is that frame check sequence at the end, and how we put items onto a media or medium, how we deal with collisions, and how we deal with retransmissions on that particular medium. Now, if you look at this picture, you will see a good example of all the different types of physical layer components that can be used with Ethernet. Back in the old days, we could do 10 base 5. This was sometimes called thicknet, but it was 10 megabits per second, baseband signaling over thicknet. And this is coax in style, and that's 500 meters and 50 ohm cabling. You had 10 base 2, which was actually 185 meters. This was 10 megabit baseband Ethernet over thin net. 10 base T is 10 megabit baseband over twisted pair, usually Cat 3, Cat 4. 100 base TX can be 100 megabits per second on Cat 4, Cat 5. And then 1000 and up, you can see we've got the CX. This is over a copper, which was short run used inside the data center for a short while. 1000 base T, at T, which is unshielded twisted pair, Cat 6, Cat 7, running 100 meters. And then we've got our fibers. We've got multimedia, and we've got the long media, or basically multimedia and multimode and single mode, sorry. Multimode fiber and single mode fiber. One is for shorter runs. You see that 220 to 550 meters. And then you've got single mode fiber, this LX, which is 550 to 500 meters. And really the takeaway here is all of the methods used for data encapsulation and for media access control are the same regardless of what media you're on with these physical layer standards. Now when you go to Wi-Fi, it uses a little different media access method. It doesn't use CSMA CD, it uses CSMA CA. So these are all carrier sense multiple access with collision detection method or medias that are in use. And what that means is the system listens to the line carrier sense. Is it open? If it is open, it sends. If there's a collision, the first device to see that collision sends out a jam packet, which causes all the other devices to do a back-off algorithm. The reason it's multiple access is because you could have multiple machines send at the same time. Now, in our modern networks with switches, collisions are almost a thing of the past unless something's gone terribly wrong. Here's the beauty of Ethernet and why it won. Watch this. In '73, it could barely move any information. And by 2016, you're looking at now 2.5 gigabit and 5 gigabit base T. So, 100 gigabit, all the way up 100 to 40 gig. So we've got all kind of crazy speeds that are available now inside of Ethernet. But they all use the basic Ethernet frame structure, which is this 8-byte preamble in the front, which signals that there is a frame on the line. The destination address, which we'll learn, is 6 bytes, which is 48 bits, which is the media access control sublayer. Let me open me up a notepad. You know I like my notepad. Can't help it. So what you're going to end up here is you've got 6 bytes for the MAC address, which is a media access control address, which ends up being 48 bits. And you're going to learn that the MAC address consists of 24 bits, the first 24 bits, which is what's called the OUI, or the organizational unique identifier. And then the other 24 bits, oops, oh, hitting the wrong button. The second 24 bits are just the device serial number. Okay, so that's how you divide up the MAC address. Now this is really important because if you know the MAC address on a device, you can actually find out who the PC belongs to or the host belongs to. In fact, one of the ways they want to bind, torture, kill the BTK killer is that the MAC address of the PC he used for one of his manifestos he sent to the police had metadata in it from Office, and it had the MAC address, which led them to the PC that had been sold to a certain, actually to the church he was part of, and that was where he used that computer to write his manifesto, and they were able to capture him. So that's an interesting little thing there. Again, here's our preamble or starter frame delimiter. My destination MAC address, which is the 48 bits. Now, it's important to recognize one of the things that they did early on is when they come up with Ethernet, is they put the destination MAC first, which is different than once you get up to the network layer. When we get to the network layer, you're going to see that the source IP is first, then the destination IP address. The reason this was done when Ethernet was created is that every machine that sees a frame go by on the line must pull that frame in, pull off the preamble, and look at the destination MAC address and make a decision as to whether or not that frame is for them. If it is, in other words, if the destination MAC address matches that host MAC address, it then will continue to take the frame apart and pass it up to layer 3. Source MAC address is second. Ether type tells you what type of ether type frame it is. Be IPv4, it's 0 by 800, 0 by 86DD for IPv6, and it happens to be an ARP request or ARP reply 0 by 806. And so there'll be an ether type in there. Here's your data, which can be from 46 to 1500 bytes. And this is where we end up with our maximum frame size of basically 1514, 1548 for Ethernet frames. And then the final item is a frame check sequence, which is a CRC or a cyclical redundancy check or a mathematical calculation run against the frame, tagged onto the frame at the end. The same mathematical calculation is run, hashing calculation basically is run on the receiving end. If it is different from the frame check sequence placed on the Ethernet frame, the receiving machine assumes that frame was damaged in transit in some way. The interesting thing about frames on our networks is that any frame under 64 bytes is considered a fragment. and it's called a runt. So if you ever do a show IP interface brief and you're looking at interfaces and it says number of runts received and there's a large number of runts, you've got a collision going on somehow. You also now have a frame. We have the ability to actually make frames bigger than 1500 bytes. And those are called jumbo frames. By default, devices will not accept jumbo frames or send jumbo frames. But in our data center, one of the things we've started doing is adding jumbo frames as an item that we configure on our switches and on our servers so that we can send bigger Ethernet frames, especially on the backplane of a data center. So as we look, and we got a wire chart that will let you look at Ethernet frames. Okay, you'll do that lab. But here, the MAC address is in hexadecimal, okay, which is base 16, 4 bits per hexadecimal digit. And if we look, the MAC address, and this is just looking at how decimal, binary, and hex. Hex is always 0 to F or 0 through 15, and ABC, A through F is used for 10 through 15 because we can't do the numbers, otherwise it looks like 1, 0. Really, honestly, for what we're doing with MAC addresses, the big thing here is you need to know this. First 24 bits or 6 hex digits are the organizationally unique identifier. And then the last 24 bits are the vendor assigned address, which is really just the serial number of the device. Now, here's something cool. I'm actually going to go in here and try to open up another. Go away. Go away. Okay. I'm going to try to open up another tab, and I will now. And I'm going to go to OUI lookup. Okay, organizational unique identifier lookup. Wireshark's got one, and you put in an OUI and look it up. So I'm going to go and I'm not going to show you all mine, but I'm going to show you. I'm going to look IP config on my own personal machine here, and we're going to look for my physical address. So we're going to look down through here, and I need to do /all. And we're going to go back up and find my Ethernet. All right, Ethernet adapter. And we can see my physical address is 90B11C. All right, so let's do 90B1, so 1C. I think that was right. Yep, 90B11C. Fine. Oh, look. What kind of computer am I setting at? Setting at a Dell computer. And you found that out because you looked and were able to search the first 6 hex digits or 24 bits of my MAC address. So that is one way that the OUI can be used. Very useful if you're teaching, if you're doing security and you're trying to figure out whether or not what particular machine may be infected, and also whether or not you need to worry about that machine. Any questions about that? Okay. So basically, you know your vendor and you know the particular device. And when you look at frame processing, this is traditional Ethernet. Well, actually, there's a switch in here, but it's sending information out to H3. It would come in, and on a modern network, this frame doesn't forward it out into a segment that doesn't have the machine on it, because the switch learns all of the MAC addresses on its individual machines or on its individual networks. Now, if for some reason the switch has just been turned on, and so the switch doesn't have its MAC address table built yet, and we'll learn more about switches as we move into the routing, switching, essentials class. But if it doesn't have its switch MAC address table built yet, it has to forward it out all ports except the one it came in on. So if source all A's sent to all C's, and that particular MAC address was not in the table for the switch, it would get forwarded out all ports except the one it came in on. Now, that means that H2 and H4 have to look at it at least up to layer 2, which is why when they built Ethernet, they were smart enough to put the destination address first in the frame. They will look at it and say, this is not me, I shall ignore it. Don't ask them while they're speaking Old English, but they are. But H3 will say, that is in fact my machine, or my address, and will then pull it up, break it apart, de-encapsulate it, run the frame check sequence on it, make sure that the frame is okay, then pull it apart, pass it up to layer 3, and then layer 3 will have to look at the layer 3 addressing to see if the layer 3 addresses match H3's layer 3 address. Now again, some different ways you can look at it or see the particular addresses, MAC addresses. It can be 2 digits and a dash. It can be colons. It can be 4 digits and a period. So multiple different ways of doing it. You can do it with dashes, with colons, or with the entire 4 digits, 4 hex digits, and then a period. Cisco routers use the 4.4.4, where X is a hex decimal. If you do an ipconfig/all, that will show you your MAC address. And if you're on Mac or Linux, you can do an ifconfig command. Slightly different. So what is a unicast MAC address? That is a MAC address of a single host. So if I'm sending to a single host, I'm going to make the destination MAC address that host address. Now, we'll learn here in a few minutes how you learn those addresses. By default, you may not know them. You may have to broadcast. But to begin with, we're going to assume that you know it by using a process called ARP, or Address Resolution Protocol. If you don't know, or if you want a particular frame to go to a large number or a big group, an entire group, you can put in the MAC address of all Fs, which I call, just imagine you're a cat making the sound. So it's the all Fs, and that is the broadcast, because really if you look at all Fs, it's all ones in every single of the 48-bit positions on the MAC address. So that is the broadcast, and it would go to everyone on the network. And in fact, the switch will never hold the broadcast address in its content addressable memory table. It will always go out to every single port. There is a thing called a multicast MAC address, and this is when you go to some members of a group, not all the members in a group. And to do that, you must have an application that is running multicast and that is receiving multicast, and then it will create a multicast MAC address that it will listen on. A little bit beyond the scope of what we're doing in this class right now. So let's talk a second about how switches work. By default, when you boot a switch up, it has nothing in its content addressable memory table. That's what the CAM is, which is also called the MAC address table. But there's nothing in this CAM table or MAC address table. As a result, the switch will have to build its table. It does that by looking at the source MAC addresses that come in frames into a port. Then it will build its table out. But because the switch has nothing in the table to begin with, it acts like a hub to begin with. So if A were to send something out, even if it knew the MAC address of B, C, and D, and it sent it in a unicast to B or C or D, it would actually come in one, and then the switch would put the MAC address of A into the port 1's information. So it'd be port 1 and then MAC address of A. By the way, they've shortened these for demonstration purposes, just so you don't have to have 48-bit addresses. But because the destination MAC address, let's say they were sending it to 000 to C, because that is not in the table, the switch must flood it out every port except for the one it came in on. Because it assumes that if it come in an incoming port, if there's another host on that link, that segment, and that host is already there, then it would have seen that particular frame. So it learns it. So here's exactly what it does. When a frame comes in, I don't have this source MAC address, and so it will flood it out once it comes in, it'll put that in, and then it will have to flood it out every single one because it doesn't know, even though the destination is 000D in this case, it doesn't have that in its table, so it has to flood it out. And what's going to happen is when D responds, the switch will be able to add that into its MAC address table or its CAM table. And so now it knows, once this table is built, A and D can send directly to one another, can send frames, and the switch will switch them between the ingress and egress, so the incoming and outgoing ports, without 2 and 3 ever having to see them. So once it's learned, everything is good. Now, obviously, we still need to learn B and C to have a fully populated MAC address table. But you can see how switches are beneficial, because the neat thing is, because of port buffering, A can be talking with D while C is talking to B, and even A can talk to D and C can try to send something to D at the same time. And the port, because it has, or the switch, because it has port buffers, will actually be able to hold that until the line out to D is clear, so we don't have collisions. So modern networks with switches really don't have collisions. I'm going to let you look at this video on your own, and that video also. But I love these activities. This is one of my favorites. So when we look at how a switch works, let's look at this and say, we have a frame. The destination MAC address is 0A, and the source is 0F. So where will the switch forward the frame? So let's look at what we know. So the destination is 0A, and the source is 0F. All right, so 0F, 0A, okay. So it comes in destined for 0A. Well, if you look in the MAC table, you can see that 0A is known, so it's going to forward it there. When the switch forwards the frame, which statements are true? Okay, so let's see, is 0F known on F9? Yep, so the switch is not going to add the source MAC address to the MAC table because it's already there. All right. Frame is a broadcast frame we forwarded to all ports. Well, we know that's not true because the destination is not FF, it's 0A. Frame is a unicast frame and will be sent to specific port only. That is true because you can see it's unicast, it's destined for one MAC address. Again, these are shortened, they're not full. Okay. And then we also have it in the MAC address table. And then we look down, teacher, you're right. It's question 1 and statement 3, because frame is a unicast frame with flooded all ports. No, you don't flood those. Frame is a unicast but will be dropped at the switch. No, that's not true either. So when we check it, correct. And then we do a new problem, and it continues to go through and give us problems. You'll notice here this one's destination FF, so it's very different. So where will this switch forward this frame? What ports? It come in port FA03 or FA3. So which port is it going to send it out to, this FF? Okay, you're saying 2. Okay. Well, remember, with a broadcast, it sends out all ports except, oh, no, okay, statement 2. Yep, forwarded all ports. That's correct. Notice this too. 0B is not in the MAC address table right here for FA03. So question 1, item 1 is also true. Statement 1 is true because it adds that source MAC address into that port. And unicast, no, it's not unicast. But the other thing is, where will it forward the frame? It's going to send it to FA1, FA5, FA7, and FA9. Because remember, it floods it out all ports except the port it was received on. Also be aware, though, the reason you don't check these other ones is because nothing's connected to them, so it's not going to send anything to a port that's down. And we're correct. And you can just keep doing more and more problems, which is a great way to learn how switches deal with frames and building their MAC address table. Are there any questions on this particular activity? All righty. A couple frame forwarding methods on Cisco switches. The two most common are store and forward and cut through. Store and forward stores the entire frame, runs the CRC on it, and then forwards the frame. So with store and forward, you're never going to send out a frame that is damaged. The frame has to be completely received, checked, ensure that it has integrity, and then you send it on. So it's a little bit slower if you don't have high-end switches because you got to bring the whole frame in, check it, and then send it out. The other method is cut through, which actually starts sending the frame before the entire frame is received. And there's two different ways to do this. One is fragment free, which is after the first 64 bytes. And then the other method is fast forward, which does it after you receive the destination MAC address. So you got fast forward, and you've got this. Fast forward, it automatically starts sending it. This is a cut through method. It sends it as soon as you get the destination MAC address in. Okay, so it begins forwarding it almost immediately after reading the destination MAC address. Now, can you send a frame that's been damaged? Yes, you can with fast forward. With fragment free, since you're receiving the first 64 total bytes, technically, due to if you're following all the rules of Ethernet, in other words, you're within your distance run limitations for your cabling, you haven't done anything weird setting duplexes and speeds or those things. Honestly, if a frame is at least 64 bytes in size, you should be able to forward it and never have a problem, because anything bigger than 64 bytes can't be a collision. So it's not a runt. Now, there could be some other things go wrong with it, but for the most part, if you get 64 bytes in, you're okay. So be aware that it's, it is available. Many of them do. Depending on the switch model, depends on what they support, versus cut through versus store and forward. Some of them are actually configured to do cut through until you reach some error threshold that you've defined, and then it will actually change over to store and forward. And then when it goes back below that error rate threshold, it'll go back to cut through. If you're getting a large number of errors on your switch ports, you've got something wrong. You need to do some investigation, because there really shouldn't be any major issues going on. Switches do have what we call buffering memory. One is port-based memory, which is memory that is on a per-port basis to be used for buffering. And then we can have shared memory, which is memory shared among multiple ports, which are all in use. And you got to think about, really, for many different types of switches, shared memory works just fine, because not all the ports are going to be in use at one time. So, duplex and speed settings. The way I describe this is, if you happen to watch the Science or Discovery channel like me, there are a couple different types of duplex, and half duplex would be when base camp is talking to somebody on the top of Mount Everest. Base camp to camp 2 over. I don't know why it's always somebody British, but it always is. They say over because on a walkie-talkie you can either send or receive. In other words, a walkie-talkie is half duplex. Full duplex, you can both send and receive at the same time. So it's like a cell phone where you can talk and listen at the same time and talk over each other. We really need to be running full duplex, because what happens in full duplex is you're sending on one side connecting to the receive on the other, and vice versa, so that when you have full duplex, you won't have collisions. And where you can really get in trouble is if you let auto negotiation do its thing. In other words, you let the switch, you do duplex auto, and the switch, one side actually configures for half duplex and one side does for full duplex. And so if you do this, you're going to have collisions. I quite honestly do not like auto negotiation on anything, pretty much. So if I'm going to set speed and duplex, I'm going to set it on a per port basis using the duplex command. Another item we kind of have out there right now on ports and on routers is a thing called MDIX, or auto cross. Auto index is typically if we connect two like devices. In other words, we connect a switch to a switch. You should be using a crossover cable. Modern switches today, though, especially on switches running iOS 12.8 SE or later, they actually auto negotiate or auto cross. So you can put a straight through cable in here, and the two switches will actually auto cross, and you won't have to worry about having a straight through instead of a crossover cable. If I got a question on an exam that asked me what kind of cable goes between two switches, and it didn't mention auto MDIX, it has to be a crossover cable. Now, the funny thing is, typically when you think about like devices, you would think, well, switch to a router, they're both networking devices, so it'd be a crossover. But that is not true. The ports on a router are considered to be network interface cards. So this should be a straight through cable, the one between the router and the switch. And obviously the one between the host and the switch should be a straight through cable. So we used to spend a lot of time, especially when we run different lower level switches, we spent a great amount of time describing crossover cables, building crossover cables and all those. For the most part now, all that's been fixed by autocross or auto MDIX. So let's talk a second about how do I send a frame if you're on the same network, the same segment. What you do is, first off, you need to know an IP address for sending something to or a reason to send something. So let's say I'm going to ping from 192.168.1.110 to 150. I don't have anything in my MAC address table. So in other words, I don't have the destination MAC address. I don't know it. We have to have a mechanism for finding that out. And that mechanism is going to be Address Resolution Protocol, or ARP. ARP allows you to send out an ARP request. So this particular host, before it could ever create this frame, would broadcast an ARP request. That final destination, since it's on the same network, would send back an ARP reply. And what the ARP request is, it says who has 192.168.1.50 and what is your MAC address, and it's broadcast out. The destination will then send back a unicast because the source is there, and it will say, hey, I'm 192.168.150, and my MAC address is 000B. Host A will put that into its ARP cache, and then it will create the frame and send it over. So if you're on the same local network, the ARP requests and ARP replies go between the original source and the final destination. It gets a little weird when you put routers in between the original source and the final destination because routers do not pass broadcasts by default. So when this particular source says who has 172.16.1.99 and what is your MAC address, this final destination of 172.16.1.99 never receives that ARP request because R1 doesn't forward the broadcast. But R1 is smart enough to go, oh, that's a remote network. And so R1 sends an ARP reply, which is a proxy ARP for the final destination. It says, oh, to get there, put in my MAC address. This is called proxy ARP. This is the process of the router proxying its local MAC address for a remote destination. Does that make sense? And Keisha? Okay, so what is ARP? It is a protocol that allows you to find out the MAC address from a known IP address. So we resolve IPv4 addresses to MAC addresses. That's what we're doing. You can also maintain tables of mappings, especially on a host. So we're going to find out. I'm going to send an ARP request to learn the MAC address of the IP 192.168.1.7. Sends out a broadcast. Everybody sees it. 1.7 responds. It can then forward its information. It has on the switch, and I'm on the host itself, there is an ARP table in the host. By default, it will keep a entry in the ARP cache for 2 minutes, and then if it's used again within 2 minutes on Windows, I think it stays in there 60 minutes, then it's flushed automatically no matter what. So it depends upon the operating system as to how that cache is actually managed. But there is a local cache. So once you do an ARP request and learn that 1.1, which is this PC or this router port right here, is this 000D, that will stay in the ARP cache for a set amount of time. So you don't have to send an ARP request every time you go somewhere out on the internet. Once that is flushed, though, you will have to do another ARP request. Okay. On a router, you can go show IP ARP and see the table. On a PC, you can do an ARP-A, and you will see different types of ARP entries, some dynamic, some static. You can actually set static entries, and there are some that are static based upon existing IP addresses that are there. For instance, the all S, they know that's the static MAC address. The broadcast address. So You have to be careful, especially if you power on all the devices at one time. You can have an op broadcast flood the local media. Not a big deal anymore with switches. I mean, still, yeah, I know it floods out all, but your switches can handle that. The bigger problem from a security standpoint is our spoofing. In other words, if I can perform a denial of service attack on the gateway and you send out a request for 1.1 and I give you my MAC address, I'm the hacker here, the evil hacker, that as a response to 1.1, your frames will then come to me as the evil hacker or to the evil hacker, and then that evil hacker can forward it to the actual destination. And this is what's called a man-in-the-middle attack. Now, there are different types of things we can do to fix this, like dynamic ARP inspection and other types of things, and port security, which we will talk about, which is probably a bigger item, an easier way to solve this problem. We can do it with port security. We'll talk about that later as we move into routing switching essentials. But just be aware there are some issues with ARP that can cause security problems. Now, folks, that is it for Chapter 5 on Ethernet. So we've talked about, the physical layer, we've talked about the data link layer, and so our next chapter will be on the network layer, and we will start moving into some of the most important items that we have, which is addressing and how to do subnetting and those types of things. Are there any questions as we continue to move forward in our class? I'm going to stop sharing. I'm going to stop the recording.